Hey guys, Miss Marusik here, and in this video we're going to talk about utilizing molarity in conjunction with equations, either a dissolving equation or a chemical reaction equation. Now in this first example here, we are presented with a solution of barium chloride where we have been given a molarity, and we're asked to determine the concentration of each ion inside of it. Now there's going to be two methods we can use to perform this calculation, and I'm going to address both of them, but both of the calculations which start off with first writing the dissolving equation for barium chloride. So barium is Ba with a positive 2 charge. Chloride has a negative 1 charge. So that means it would take 2 chlorides to balance out the barium. And when that dissolves, we'd end up with barium plus 2, that's aqueous, and 2 chloride ions that are also aqueous. Now, you wouldn't necessarily have to put the states in order to solve this problem, but you should be showing the charges as well as the coefficients with those two ions. So first off, let me show you type number 1 of how to solve this, and that is by utilizing what is called a Rice table. Now, a Rice table stands for reaction initial change and ending. We utilize Rice tables a lot in the spring when we get to our equilibrium unit, especially when the concentrations of things aren't totally going away or totally appearing in a perfect mole-to-mole ratio. Here it's a little bit easier because they are in a mole-to-mole ratio, but it's still a good method to show our work if we're doing an F or Q question. So how this works is that I would first start off with my initial concentrations. Before I dissolve, I would have 1.50 molarity of the barium chloride and none of the barium or chloride ions. So then my change is that this barium chloride concentration is going to totally go away. This is going to totally split up into ions here. And so as that disappears, I would end up with no molarity of it at the end. However, these two ions are both going to go up in mole-to-mole ratios that correspond with the original barium chloride. So since barium chloride and barium are in a 1-to-1 ratio, this will go up by 1.50, meaning at the end I would have 1.50 molarity of the barium ion. And for the chloride, this would go up in a 2-to-1 ratio. So 2 times the 1.50, meaning at the end I would have 3.0 molarity of him. So by utilizing that Rice table, I was able to figure out that the concentration of barium was 1.50. By the way, if you want to show concentration, you can use brackets around something. So showing brackets around Ba positive 2 would indicate the molarity or the concentration of that ion. And then my concentration of my chloride ion would be that 3.0 molarity. So you can see I got both my ion concentrations at the end. Now, that is one way of showing that work. Another way that you could show the work instead is by using a stoichiometry setup. Now, I'm going to only do this for one of the ions just so you can see how it works, and then you can take your pick on which of these two methods you like better. So this would be method number 2. I would first need to write my balanced equation just like we did up here. I would need to show my dissolving equation. And then what I could do is I could say, hey, the concentration of chloride ion would be equal to the 1.50 molarity BaCl2 where I apply the mole-to-mole ratio. So applying the mole-to-mole ratio here, just like I would for reaction stoich, I would say that for every 1 mole of BaCl2, there are 2 moles of chloride ions. Now, if you're wondering how the units cancel out here, don't forget that molarity is the same thing as reporting moles over liter. So the moles of barium chloride are going to cancel out top and bottom, leaving me with moles of chloride over liters, which is my 3.0 molar solution of the chloride ions. So you can see it got me to the exact same answer here. It's just a different way to approach the same problem. All right, on the next one, they kind of shorted us a little bit of information. It's the same type of problem, but what we're first going to have to do is address the fact that they didn't give me molarity of the iron 3 perchlorate. Instead, they gave me grams and milliliters. And so what we need to do first is actually solve what my molarity should be. Now, as a reminder, molarity is moles over liter. However, in place of moles, I could substitute in mass over molar mass, which is what I'm going to have to do here because they gave me the mass of iron perchlorate instead of just giving me moles off the bat. All right, so I'm going to go ahead and plug into that equation to solve my molarity. So my molarity of the entire solution would be 30 grams. Now for iron 3 perchlorate, I would need to solve its molar mass, meaning I need its formula. Iron is Fe. Perchlorate is ClO4. Now, this 3 means I have a positive 3 charge on the iron. Perchlorate has a negative 1 charge. So to balance out the positive 3 and the negative 1, I would need 3 of those perchlorates. Now, I actually already have the molar mass of iron 3 perchlorate. You would need 1 iron, 3 chlorines, and 12 oxygens all added up. And that gets a molar mass of 354.2 grams per mole. And so then I would take that and divide it by my liters. Now I do have milliliters, so I would need to convert into liters. So I'm going to move that decimal place over 3 spots. And so now what I'm going to do is I'm going to plug in this math here first. 30 divided by 354.20 divided by my 0.3 gets us a molarity of 0.282. So again, this is the molarity right now of the FeClO4-3. But what it wants is the molarity of each individual ion. So what I want you to do is pick a method real quick and see if you can now solve the molarity of each of those individual ions. So go ahead, pause the video, try it out. Did you try it out? I hope you did. All right, I'm going to go ahead and put what I got for my answer up here. I did use the Rice table. You could have just as easily done this utilizing stoichiometry, would not have made a difference. Okay, but in setting up a Rice table, I first showed my dissolving equation. So even if you were doing stoich, you would want to make sure to do that dissolving equation first. And then I said, hey, all of that iron 3 perchlorate is going to go away. It's going to be 0 at the end. Both of these are going to go up in a mole-to-mole ratio equivalent to that. So 1 to 1 here between iron 3 perchlorate and the iron would mean I would also have 0.282 molarity of the iron. However, having a 1 to 3 ratio between the iron 3 perchlorate and the chlorate ions, I would want to multiply that value by 3. And so that got me 0.846 molarity of the chlorate ions. So again, if you did it via stoich, you should have gotten exactly the same thing, just a different way to approach it, as long as you're showing that work in some form or fashion for some sort of free response question. All right, let's go ahead and look at the next page and how I would use this with reaction stoich problems. Okay, so what I have here is it says I have a bottle of hydrochloric acid was found on the shelf, but was missing the molarity value on the outside of the bottle. Tisk, tisk, that's no good. It says in order to determine the molarity, the acid was standardized by titrating it with the known mass of sodium carbonate. So I can see here that I have a reaction that's occurring. They're giving me amount of one thing, they're asking me about amount of another. I'm going to go ahead and kind of start that process of a reaction stoich. Now what I did here is I went ahead and wrote out my balanced equation. So it said here we had hydrochloric acid and sodium carbonate. When I have a compound and a compound like that, I assume that they do a double replacement reaction. So the hydrogen and the carbonate would pair up to give me H2CO3. The sodium and the chlorine would pair up to give me NaCl. Now I will mention this kind of just as a side note. When we get to reactions, you'll find out that this H2CO3 does further decompose into carbon dioxide and water. However, it's not necessary to do that further decomposition here, and so I'm going to just leave the reaction just like so. However, what I'm going to do is I'm going to kind of start to map out here the information that they give me. They tell me I have 25 milliliters of hydrochloric acid, And they say I have 0.129 grams of sodium carbonate. And they want to know what is the molarity of the acid here. Now think about this for a moment. To get molarity, I would need moles over liters. That's the unit of molarity, and if I divide those, I could get my molarity value. Well, I kind of already have one of these pieces. If I convert milliliters into liters, I already have that value. So what that means is that I want to use Stoich here to figure out my moles value. And so what I'm going to do is think about reaction Stoich. To get between one substance and another, I would need a mole ratio here. And to get between grams and moles, I would want to use molar mass. So what we're going to need to do is use Stoich to get us from the grams of sodium carbonate to the moles of HCl. So then once I have those moles of HCl, I can divide it by the volume in order to figure out what my molarity would be. All right, so I'm going to go ahead and start my stoichiometry work here. So again, I'm trying to figure out how many moles of HCl are equivalent to the 0.129 grams of Na2CO3. So I would need the molar mass of Na2CO3, which when I calculated that value, that got me 105.99. And that would be for 1 mole of Na2CO3. And then I would need to do a mole-to-mole ratio. 1 mole of Na2CO3 for every 2 moles of HCl. Again, I'm utilizing those coefficients there. Okay, so what I'm going to do is I'm going to plug that into my calculator and see what that gets me. So 0.129, 1 over 105.99. 2 over 1, and I see that gets a value of 0.00243419, yada, yada, yada. Okay, so what I'm going to do is I'm going to write down 0.00243419, yada, yada, yada. Okay, I'm not going to round for sig figs yet because I'm about to do some more math to this. So this is that moles of HCl. However, what I would want to do now is, as we said a minute ago, is that I would want to divide this by my volume. I would want to divide it by 25 milliliters. However, I want to do that in liters, and so I would want to divide it by 0.2500 liters once I move over that decimal 3 places. So dividing it by 0.02500 would get me a value of 0.097, and I'm going to round this for, let's see here, 3 sig figs because my mass had 3 sig figs. So I'm going to use 0.0974, and that would be my molarity of my HCl. All right, let's go ahead and look at another problem here. The next one says, hey, what volume of 0.955 molarity hydrochloric acid in milliliters will be needed to titrate, meaning react with 2.152 grams of sodium carbonate to the equivalence point? Now, luckily for us, this was the same exact equation we saw just a minute ago, except that we have different pieces of information now. So it says, hey, for hydrochloric acid, we have 0.955 molarity, which is the same thing as saying the moles over the liters of it, okay? Then it says I have of the sodium carbonate 2.152 grams. And it wants us to figure out this volume in milliliters. So eventually, I want to take this liters and figure out how many milliliters to it. Okay, well, if I think about this molarity equaling moles over liters, if I figure out what the moles are, I can figure out what the liters would be, right? Doesn't sound so bad, okay? So what that means here is that I'm actually trying to figure out the moles. which means I would need a mole-to-mole ratio. And I would want to work grams to moles utilizing the molar mass again. However, I am going to share something with you as kind of a trick of how you could do this. Once you figure out that 0.955 molarity is moles over liter, you don't have to just stop at moles and calculate this molarity. What you could do is use the molarity as a conversion factor. So I'm going to actually show you how to do it via that method because I think for some of you it might save you some time. Now, could you go ahead and stop at moles and then plug it in and solve for your volume? Absolutely. But I'm going to show you kind of a quicker method to do this. Okay, so what I'm going to do is I'm going to start off with my 2.152 grams of Na2CO3. And just like we did in the previous problem, I'm going to start off with my molar mass, 105.99 grams for 1 mole of Na2CO3. And again, then I would say, hey, for every 1 mole of Na2CO3, there are 2 moles of HCl. Okay, so now, could you stop here? Calculate moles, plug it in here, solve for the volume, and get an answer? Absolutely. But like I said, I'm going to show you kind of a sneaky way that you could do this. So I'm going to actually continue with my stoichiometry here. And what I'm going to do is I'm going to use this 0.955 molarity as a conversion factor. That 0.955 molarity is the same thing as saying 0.955 moles for every 1 liter of solution. So I'm going to utilize that as a conversion factor right here. Now, since I had moles of HCl on top, I want moles of HCl on bottom. So I'm going to say 0.955 moles of that HCl for 1 liter of that HCl on top. Okay, that would give me into liters. Now I'm going to go ahead and add a step on here to get my liters into milliliters. This would be a metric conversion. 1 times 10 to the -3 liters equals 1 milliliter. 1 goes with the prefix. Milli is 10 to the -3. And so now I could plug all this into my calculator. So you can see instead of stopping back here and then solving a molarity problem, I'm kind of connecting all the pieces together to save myself some time on the calculation. So I have 2.152. Open parentheses, 1 over 105.99. Then I have 2 over 1. Then I had 1 over 0.955. And then I had 1 over 1 second E -3. Hit enter, and I see that gets me 42.5 milliliters. And actually, let's see here. Ooh, I need 3 sig figs because the 0.955 only had 3 sig figs. So I'm going to show 42.5 milliliters of HCl that I would have needed in that reaction. All right, hopefully we are not feeling like chemistry cat down here. Hopefully we are not going to have to calculate the molarity of your tears on your AP chemistry test. Hopefully we're feeling confident with doing calculations involving molarity. All right, if you have any questions or need any help, please feel free to email me. Bye, guys.